下礼拜一的考试我们会是不看书的 ，OK？ 因为电磁学是很基本的课，有些东西你的确要记住。但是呢，你如果需要任何的公式、数学式子做计算的话，你随时可以举手问，然后呢，我们会帮你写下那公式，你需要的公式，然后让你算。All right？ 所以基本的概念你要了解。所以这是一般大学部的课的话呢，比较不倾向于开书考试 ，OK？ 所以上回我们讲到这个 electric dipole，well，basically electric dipole consists of two charges， 两个电荷在那个地方 ，with a separation of d in space。Usually what we care is the far field from this electric dipole, because almost all the applications in engineering we just calculate the far field from an electric dipole. 因为呢，这个在一般的物质里头是中性的物质，是 neutral 的这个 particle, so usually it consists of two charges. But very often that these two charges with equal sign, with equal amount of charge with opposite sign, are separated with a distance d. 那这个 d 呢，让你在远处的地方你可以量到一个电场。Okay, suppose that this d is equal to 0. 假如是完全中性，而且这个 d 的距离是等于0的话呢 ，basically this charge is going to compensate with this charge exactly in space. And then you don't get anything in the far field or even in the near field if you have two opposite side charges overlap exactly in space. Okay, so this d is very important. And based on this far field approximation, last time on Monday we calculated the electric potential at a distance r that is much larger than d. 在这种这个 far field 原场的这个特性之下呢 ，you can get this expression for your electric potential. Okay, and let's take a look at the property of this expression, but not just memorize it. Okay, number one, I told you previously that this is a 1 over r squared dependence in this electric potential. For a single charge in space, the distance dependence is going to be 1 over r, not quite 1 over r squared. This 1 over r squared is because that the two charges with opposite sign compensate each other to some extent. Therefore, you have r squared dependence here. 因为这个两个电荷的这个电量一样，距离很短，所以呢，它互相弥补掉一些。所以呢，它的 electric potential 不像单一电荷那样子是 1 over r 的这个 dependence， 它比较弱了，变弱了。For big R, r square usually is bigger than r for large R. Okay, 像 if r is equal to 2 meter, r square is going to give you 4 square meter, right? Is getting bigger. Therefore, this electric potential is going to be reduced more because of this arrangement. And another thing is that there's just define a new variable called the electric dipole moment. It's defined to be the charge multiplied with the separation of the charge. And there's a direction associated with this electric dipole moment. It's a vector, and the direction is defined from minus charge to the positive charge. And be careful that the definition of the direction is just opposite to the definition of electric field. For electric field, you always originate from positive charge and point toward the negative charge. But for this electric dipole moment, 这个方向呢是从负的电荷到正的电荷 ，so don't be confused. Okay, you have to follow the definition to get the right answer. So for this electric dipole potential is going to be expressed by this very compact form with a P dot AR. This dot product is going to give you an angle dependence. OK， 所以这是 electric dipole potential 的这个一个式子。And based on an approximation that the R is much larger than D. And I want to show you why we have to study this. As I mentioned to you several times, most of the situation in this world is neutral. Now that it's neutral, why we have to study this charge separation induced electric field in the far zone? The reason is that when you have two neutral, for example, one example is that when you have two neutral atoms move together, 即使它是完全中性，但是呢 because there's a positive charge and negative charge in this particle, and there's also positive charge and negative charge in this particle. When they get together, they are going to redistribute the charges because there's a positive charge inside, negative charge inside. The positive charge inside this atom is going to attract the negative charge inside this atom, and then you have redistribution of the charges to form this electric dipole. So there's a quite short animation of this kind of situation when two atoms approach each other. Then there will be a redistribution of the charges. So I want to show you this sort of movie, but I need to log on first. So 所以我先把这个 OK, let me log on this. Oops. So in this movie, you're going to see approaching. You're going to see approaching of two atoms. 两个这个原子会慢慢接近，每个原子呢，它都是电中性的。Okay, one is a hydrogen atom. Okay, denoted by this blue dot, and then another one is chlorine. 是氯原子，much bigger than the hydrogen atom. And this one is neutral. This is also neutral, but it means that there's a lot of positive charges, proton inside this atom, and also a lot of electrons inside. When they move together, you're going to see that this positive charge and this is going to attract negative charge from this big atom. Also, those positive charge are going to attract negative charge from this hydrogen atom, and then as a result, you form a hydrogen chlorine bond, but you have redistribution of the charges, slightly more positive on this side and slightly more negative on the other side. Okay, so let me show you again. So in nature, when two neutral particles, neutral atoms approach each other, the charges, especially electrons in atoms, will be redistributed because electrons are very light, very easy to move. Okay, so again, this is a hydrogen atom with one proton and also one electron in this atom. And for chlorine, 氯的原子, there are lots of charges inside with a large amount of proton charge and also a large amount of electron charge. When they approach each other, then the the positive charge here is going to attract the electrons from this hydrogen, and this hydrogen proton is going to attract the electrons to this side, and then all the charges become distributed with a little bit more positive on this side and a little bit more negative on this side, and effectively you have an electric dipole. OK， 你有一个 electric dipole， 把这个基本上这个正负电荷分开了。那所以呢，这个dipole 呢影响到很多的化学反应，还有很多的这个物理的这个现象。And that's why we want to talk about electric dipole. Okay. Now that you have the electric potential, you are in the position to calculate the electric field through gradient of this electric potential. And this is just mathematics. You can just look up the table and then convert this electric potential to electric field by doing minus gradient of electric potential to get your answer. Okay. So you end up having this kind of R dependence and also the angle dependence. And be careful that when we deal with the single charge, at distance of R, your electric field is proportional to 1 over R squared along R direction, right? And your electric potential is proportional to 1 over R. Now, when you deal with the dipole field, when you deal with the electric dipole, you have R squared dependence right here, okay? And now you are seeing that for the electric dipole field in the far zone, when R is big, you have 1 over R cubed dependence right here. So when you deal with dipole, your V is proportional to 1 over R squared, and E is proportional to 1 over R cubed. Okay, and this is because of partial compensation of the charges of opposite sign. 你有正负电荷，所以它互相弥补掉一些，所以呢，它的这个它的场，它的这个electric potential 掉下来比较快。Okay, so whenever you have a formula, try to understand it, but not just memorize it. Okay, once you have the R dependence and theta dependence, then you can just draw the line, electric field line or the equipotential line to visualize how the field or energy is distributed in space. Now, let's look at this. Well, if I want to find the equipotential surface, by definition, this V is a constant, right? 等电位面基本上就是设定你的这个电压呢是一个常数。And then you find the dependence of R and theta. Now you can draw the equipotential line. 这实线部分 the solid line is your equipotential line. If you set a different constant right here, you get different line. Okay, and the two charges are here: positive charge and negative Q, positive Q and negative Q. So right in between, at the center, definitely there's an equipotential line. Okay, and then extend all the way out, and also extend all the way out. For this family of curves, you have V larger than 0. For this family of curves, you have V less than 0. 这里的电位小于0，因为这是负电荷，你带一个正电荷过来的话，不需要做功，你可以得到能量。Therefore, your V is less than 0. But this is positive charge. If you bring a positive charge from far away to this somewhere in this region, you have to do your work to bring the charge to this location. Okay, 所以呢，这里的 V 是大于0。所以所有的这个数学式子都有它的物理意义。You have to understand it. Okay, good. Now, if you want to understand the distribution of the electric field, then we can draw electric field line. 我们在最刚开始的时候呢，最早期的时候 ，How do we define an electric field line? How do we define an electric field line? If I go back to chapter 1, there's a definition for the electric field line. So everything is predefined. Okay. Electric field line was defined to be direction and length. 这个方向呢，基本上就是单位正电荷所受力的方向。还有呢，这个长度 is proportional to the strength of electric field. OK， 所以它有个方向，有个长度。那长度呢是它的这个跟它的强度成正比。所以 if I want to draw a line, a differential line to represent an electric field, then this line is going to be proportional to a constant factor multiplied with electric field. Right? So let's do it. So let's do this calculation. We have the electric field right here, and then do this calculation to construct the path along E direction. And this length is proportional to the local strength of the electric field. Okay? So if you look up the textbook, starting from this concept, you can derive this expression. Just put this into this equation. And then you can derive this expression to describe the electric field line. 这个 electric field line is denoted by this dashed lines. 这个虚线部分 OK， 那从这里到这里很容易 electric field line going from positive charge to a negative charge along this direction. But don't forget that your dipole moment is going to be in the opposite direction. Okay, from negative charge to positive charge. So electric field line from here to here is a straight line downward and then go out like this. Okay, and electric field line come down and from positive charge to a negative charge. Okay, 那这个 operation, 你如果看 electric field equal to minus gradient of V, think about the definition of this gradient. The definition of this gradient tells you that this electric field has to be perpendicular to the equipotential surface of V. If you remember the definition of gradient of V, this is along the derivative of V along the normal direction, and this is along the surface normal direction. So this gradient of V is along this surface normal direction. Okay, so this means that if you construct the electric field line, this is proportional to electric field, right? So if you so this means this is electric field is along this direction, and this is the V equal to constant surface. So if you want to construct the equipotential surface and the electric field line correctly, then you have to specify a right angle at the junction of these two lines. 所以呢，譬如说这条线跟这条线，这条线跟这条线呢，它这里一定是直角。OK， 这条线跟这条线这里一定是直角。OK， 所以你这个实线跟虚线呢，它中间交界的地方一定是直角。OK， 然后呢 ，electric field line 一定是从正电荷到负电荷。OK， 所以你会画这些这个 equipotential line 跟 electric field line，right？ 注意这个直角的关系在那个地方。OK， 你必须留意到，就是说，one thing you have to be careful that when we derive this expression, and when we derive this expression, there's one approximation down here. R has to be larger than D. 这代表说你在 你在画这个面的时候，当你设定这个等于 constant 的时候呢，当 r 接近这个区域的时候，它其实是不准的。You cannot just use this expression to plot the field in this region, because you have one assumption that is r much larger than d. D is the distance from this charge to this charge. 所以在这个地方，在这附近，你用这个式子跟这个式子去画的话，会画不准。你必须用你的物理的概念去画 ，OK？ 所以这个式子跟这个式子 only valid when r is much larger than d in this region. OK？ 在这个地方你要怎么画呢 ？Well， 这个地方的画法呢，你知道，在这个地方，正中央一定是一个 equipotential 的 surface。这里的电场呢，一定是从正到负 ，OK， 所以这是你可以稍微画出这个区域 ，but you don't want to follow exactly this expression or this expression. Okay. So this is the electric dipole. So after this point, we learned about calculation of electric field, electric potential, and in fact, we can summarize the technique to calculate the electric field and electric potential. Number one, you can use Gauss' law to calculate electric field. So just like in this example, you can use Gauss' law to calculate electric field and eventually get electric field equal to 4 pi epsilon naught r squared and q. And this is along AR direction. Well, the reason we can use this Gauss law to do this calculation is because we know from symmetry the magnitude and the electric field on this surface, or the magnitude of this electric field on the surface is a constant because of symmetry. 因为它是完全圆对称的，所以这一点你没办法区分这一点跟这一点，因为对这个 charge 来讲，这一点跟这一点是完全一样的，只要是在一个这个圆球上头。Therefore, we understand that this component is a constant at the constant r. Okay, and how about direction? Well, also from the symmetry, the direction has to be along r direction. I argue with you that if somebody told me that there could be a field along this direction, then the other person can tell me that there could be an equal probability to have an electric field along this direction. To settle this argument, we compromise that the electric field only along r direction. Okay, only along r direction, either this direction or this direction, depending on the sign of this q. Okay, so there's a rule to use this Gauss law for calculating the electric field. The rule is if all the field vectors of equal magnitude are along the surface normal of a volume. Okay, we know that the electric field on this surface are all equal at a constant r because of symmetry. 所以这个面呢，你可以找出来在某些问题里头可以找出来，这个 surface 叫做 Gaussian surface. Okay, and you need to have a symmetry in one of the three coordinate systems. 这时候呢，你在计算这个electric field 的时候 ，you can do this. Because this turned out to be a constant, if you know the electric field is along the surface normal direction, this dot product can be removed. Right? This dot product can be removed. But in fact, there could be positive or negative sign associated with it. And then second thing is that you determine this electric field is a constant. So you can pull out this electric field and just do this surface integration. And then eventually, you end up having a result that this constant field is equal to Q, could be positive, negative, depending on the direction of the surface with respect to this electric field. Sometimes this electric field is going this direction. Sometimes this electric field is going along this direction, and the direction of the surface normal is always outward. Okay, that's why you could have positive, negative sign, and then you divide this with whatever you calculate from this surface integration. And don't forget that you have a vacuum permittivity associated with it. So this is how you calculate the electric field by using Gauss law. Important thing is that you need to find the Gaussian surface where all the electric field on the surface are the same and along the surface normal direction. OK， 所以这是一个方法。另外一个方法呢，我们说 you can do a integration step by step from a line, from a surface or from a volume by using this well-known expression for a single charge. 你已经知道一个点电荷在某个 r 的位置的 v as a function of r, e as a function of r. And you can use calculus to integrate a lot of points along the line contribute to this point. Okay, therefore you can construct an integration like this. Okay, coming from this expression. Right, coming from this expression because this Q is the integration of charge over, say, a volume, a surface, then you integrate over a surface. Or you can integrate this line charge over a line, or you can integrate a volume charge over a volume. Okay, but be careful that when you integrate the charge along something on a surface or on a line or inside volume, you have to integrate over the location of the charge. And the location of the charge is described by the prime coordinates. 这个 source 电荷的位置或将来电流的位置呢，它的位置是用 prime 的这个坐标系统来描述。所以呢，你积分的时候，你必须积这些这个有 prime 的这些位置，而不是。比如说积这里没有用，因为这里没有电荷。Okay. So this is the integration of the point charge point by point over some surface volume or from over a line. But I point out to you that the integration has to be at the location of the charges. Okay. And also for electric field, you have to take care of the vector, the direction of the electric field. So this is not trivial. Okay, it's just not. It's not scalar. You need to take into account the directions. 方向你必须要注意。比如说，这个的 r。从这里到这里的这个 r 跟这里到这里的 r 是绝对是不一样的。你这两个向量要加起来的时候呢，你必须做一个，比如说平行四边形，去把它加起来。OK， 把它分成，譬如说你知道，如果在一个面上的话，分成这个直角的两个方向，然后把它加起来。所以 very often that you have to decompose this into several directions and then integrate one by one. Another way to calculate this electric field with the arbitrary distribution of charges is that you can start from the electric potential. 在这个计算里头 you don't have to worry about directions. Okay, you don't have to worry about the vectors. This is pure scalar, so you just do a charge integration over the prime coordinate system, over the distribution of the charges, and then later on, once you have the electric potential, then you can calculate the electric field from this expression. 所以这是基本的两个计算 electric field 的方法 ，okay? And very often that if you cannot find the symmetry, you have to do this and then take this gradient of V and put a minus sign to get your electric field. Okay, 所以这两个方法你都要会用。我们来给你几个例子。Okay, the first example is that suppose you have an infinitely long line charge. 有一条线。这个线呢，很长很长，非常的长，让它变成无限长。OK， 在这种状况之下，你能不能找到这个一个Gaussian surface来做这个计算？哇，如果说这个线是无限长的话，你知道一个点电荷。Well, suppose you have a line with infinite length, and then you want to know the electric field at this location, for example, okay? And then you pick up one charge right here. Then you're going to have this kind of electric field from this charge. But on the opposite side, you also have another charge located to the opposite of the symmetry point to give you your electric field along this direction. So you notice if you have a uniform distribution of the charges, this electric field is going to be the same as the electric field here. Okay, so I should plot this with equal length. 然后呢 if you decompose this vector into this, well, the plot is not so well. And then decompose this vector into, again, two components. These two components supposedly has to be cancel each other, but my plot is not good enough. So let me redo it. So the symmetry point is right here. So this, because this point charge and this point charge carry the same amount of charge for the same length, so the electric field here and here will have the same magnitude, but the direction allows us to decompose each of the electric field into two components, and it turns out that these two components will be canceling each other, resulting in electric field along this direction. Okay, well, you can pick up a different point in space, and you can always find out if you pick up one charge on this line, you can always find out another charge of equal amount located from the same distance with respect to the symmetry point. Okay, so you know that for constant r, you always have a radial direction of electric field. 它的 electric field 永远是都跟这条线互相垂直，而且在同一个 r 的距离呢，这个电场强度会是一样。So given this, you can construct a Gaussian surface like this. On the surface of this cylinder, the radial component of electric field are all the same, and along the surface normal direction. So this satisfies the condition to use a Gauss law, the Gauss law to calculate the electric field, right? Now you find a Gaussian surface on which you have equal magnitude of the electric field on this surface, and all the field vectors are along the surface normal of the volume, except this surface and this surface. 在这个面上头跟这个面上头呢，它的电场跟它的 surface normal 是互相垂直的，所以 when you use Gauss law to do this calculation, Q, you have to separate this into two terms. One is along r direction, dsr, plus, well, you know this is electric field is along r direction. For this surface and this surface, your surface is along z direction, right? So this is plus minus z, az, dsz. You are doing this cross-surface integration. So you have to take into account the surface, the radial surface. At the same time, you have to take into account the surface along z direction, positive z direction and minus z direction. Okay, but you know this dot product ER dot with AZ is equal to 0 because of this 90 degree. Cosine 90 degree is equal to 0. So basically you drop out this term. You only have to calculate this term. Okay, and so if you integrate over this surface, it's going to be equal to 2 pi r multiplied with, say, a length of L from here to here. And on the and then this is E of R. On the right hand side, you have line charge density multiplied with L divided by epsilon naught. Okay, this is the total amount of charge inside from here to here. So there's a line charge density associated with this line. Okay, so this calculation is very simple. On the right hand side is the line charge density multiplied with the length of the line from here to here, and then you have ER multiplied with the SR, 2 pi RL. You end up having the electric field like this. Okay, the reason we can have this Gaussian surface is because this line is infinitely long. Suppose we have a line with a finite length. The story is going to be different. OK， 你如果有一个这个固定长度的线的话呢，这个故事就变掉了。为什么？我们把这个剪掉，把这个剪掉，从这里剪掉，这里剪掉。你如果去算这一点的电场的话，完了，你，比如说你这一点电场是来自这里，但是呢，这个的对称点的电场给你一个电场从这里过来。These two electric field are not going to cancel in the transverse direction. OK， 这个比较远，这个比较近，所以呢，这里呢比较小一点。But the net electric field is going to have one component along this direction, one component along this direction. OK. And you don't have this kind of cancellation in the transverse direction. 所以你如果挑出哪一点的这个位置的话，你必须用这个积分的方法，一点一点的积出来之后呢，重新建构这里的电场。So you can tell that the easiest way to calculate this is to do this calculation. Given the point in space, and then you calculate the voltage, the electric potential, at this point, and then take a minus gradient of electric potential to get your electric field. But if you only care about the electric field right in the middle plane, 你如果只在乎它的这个 electric field 在这个 middle plane 的话，那你知道这里跟这里的这个相消是存在的，那你的 electric field 呢会是这个方向。Okay, so in this example, I give you a calculation for the electric field at this point, right at the midplane of this line. Okay, 那这个因为在这个 midplane 上头 ，so you can do a calculation. Pick up the electric field equal to 4 pi r minus r prime square, and this will be the line charge density, and you have to integrate over dz prime, this distributed over z direction, okay, and do an integration. But you need to be careful that the direction is ar minus r prime direction. The whole thing has to multiply with the direction because it is a vector. Okay, let's first figure out this r minus r prime. R, basically r, if I'm integrating a charge right here. Okay, so from here to here is called z prime along z direction. Okay, and we're interested in calculating the electric field at this point. So R is a vector from the origin to this point. Okay, and so the distance r minus r prime basically is this. Now it's equal to r minus z prime. It's from here to here. The magnitude of the length from here to here, you can do it easily, right? This is equal to z prime square plus r square. 这个平方加上这个平方 Okay, and the integration is over z prime. And how about the direction? Well, the direction is that whenever you pick up a point here, then you can pick up another symmetry point somewhere here to get the electric field along this direction. Right? And again, you have cancellation. You have cancellation of the field along transverse direction. So what you care is the field along this direction. OK， 这个方向上的电场，假设这是这个角度叫做 theta 好了。这个方向上的电场基本上是这个方向上的电场的投影。So what I need to do is that I know that the electric field here is along r direction. So let me convert this to be r direction. And then take out this, multiply the whole thing with cosine theta. But there are 2 points, up and down. So I have to multiply the whole thing with a factor 2. Because you sum over this 2 field from this 2 symmetry point. 所以你基本上是先算，比如说一根过来的电场的大小，把它投影到这个方向上头来，但是因为上下有2点，所以你乘以2。That's it. Very simple steps. OK， 那我再讲一次，你先算一个电场从这点过来这个电场的大小，但是你知道这里有一个对称点， 所以呢，它电场是往上，所以它垂直方向电场消掉了。所以你在乎的只是这个电场投影到这个方向上的电场。Therefore, you multiply with this cosine theta. But because you have 2 points, so you multiply with a factor 2. Then we come to worry about what cosine theta is. Cosine theta is very easy to calculate, right? Because cosine theta is basically the distance from, this is theta. So cosine theta is basically equal to z prime square plus r square. And then if the distance from here to here is r, then this is your cosine theta. OK， 所以呢，你算出来，你的式子基本上就这个样子。我刚刚这里用大的 r， 这个大的 r 基本上就是等于 r a r。OK， 所以这里呢，你可以把它变成小 r 的平方。这个 r 的定义原来是在原坐标里头，因为我们是在讲一个点电荷 ，OK， 但在这里头呢，有这个坐标系统是小 r z 跟 theta 的坐标系统，所以这个大的 r 在这里是小 r 乘上 a r 的方向。Okay, therefore you have cosine theta equal to this, and then you have this integration. Now you can look up a table to work out this integration. Okay, so this is sort of one example to tell you how to use the Gauss surface and how to use the distributed integration to get your electric field. Another example to use the Gaussian surface to do the integration is like this infinite charges, infinite plane with some charge density. All right. Suppose that you have an infinite plane, very very big, with a uniform charge density of rho s. Well, on this plane, the direction of the electric field has to be normal to the surface. 因为它是无限大，所以呢，你如果告诉我说这里有一个斜角的这个电场的话，我会说它有同样的几率在另外一个方向上头有一个。那结果呢，你唯一的这个电场就是 along the surface normal. Okay, so you create a Gaussian surface that is a pure box like this, enclosing, okay, create a small box like this, and then your surface. This infinite plane is sort of in between. Okay, let me do this. I only have one box. 我们看上面这个，你可以产生一个四方形的这个 box， 非常接近这个面，上面下面都有。这个面呢就穿过这个 box 的正中央。Okay, because all your electric field is along the surface normal direction. You only have to integrate this surface, okay? Because this surface has a direction along this direction, but your electric field is along this direction. Your dot product right here is equal to 0 for this surface, for this surface, for this surface, and for this surface. You only have to do calculation for this surface, because on this surface, your electric field is along the same direction of the surface, okay? Same thing for the small box underneath. You only have to calculate the dot product surface integration along this direction. For all the sides, you don't have to do the calculation. Okay, because the surface direction and electric field direction are perpendicular to each other. The dot product is going to give you 0. So you only have to calculate two surfaces, one on the top and one on the bottom. Okay, so you only have to do this surface, top surface integration and bottom surface integration. And then the total charge is going to be the area multiplied with the surface charge density. So with this calculation, you end up having an electric field along z direction with this magnitude. But be careful that the direction of the electric field for the top surface is along positive z direction, and the electric field on the bottom is going to be along minus z direction. Okay, so this is a calculation for the electric field nearby an infinite plane. This calculation is going to be important later on when you calculate the electric field for a parallel plane capacitor. 你在算这个平行电容板的这个里头电场的时候呢，这个计算这个式子会在哪来用？所以回去做一些练习。我们下礼拜一的考试就到这里为止。那基本上相关的观念你要懂 ，OK？ 所以下礼拜一10点10分我们会在这里考试，期中考。那在这之前的话，你如果有任何问题的话，欢迎你跟我联络，或者是跟助教联络 ，OK？